So we've been discussing about the adiabatic and non-adiabatic. I was explaining this way as it is like now. And here there was no input and there was an output, plus there is no accumulation because we are running the system in a continuous operation, plus the disappearance by the reaction. So this heat should be like involved here, but in the case of the enthalpy outlet, it says that the actual enthalpy which goes out with respect to the conversion of A, so that is the product enthalpy plus the reactant enthalpy, which is 1 minus XA, which will actually give the feed enthalpy. So this is the actual enthalpy which is going out of the system. And the next one is the reaction. So the enthalpy or the energy that is actually absorbed, or if it's absorbed, then we put plus HR, delta HR1. But if it's released, it's exothermic, then we put a minus H, delta HR here. So this is a delta HR into XA. So how much conversion it takes, that much reaction heat it's been liberated here. So you sum up this, and here the system is actually being very, closed. In a closed system. So we don't have any input in the system. So this is a closed system. Once you actually derive all this, we will get an relation between conversion versus the temperature. Okay, this with respect to the specific heat of the system. So this is a heat required to rise the feed stream. So this is the heat required to rise the feed stream to a particular temperature to the heat released by the reaction. That was the ratio here. So heat supplied or heat being required for the system divided by the heat which is being released in the system. So if it's a more and more conversion, then the delta HR will be high. So this value will actually support it. So here it is in the negative sign. That means if it's more and more conversion, then this value will be in the negative sign, which will be higher. That means you will get a very high value of this because it is the negative. Similarly, if you go with the non-adiabatic, if you come in the non-adiabatic, we actually have an excess that the heat should be added or released into the surrounding, that we need to include it. So if you start to write the enthalpy balance, we have the particular the product which is converted, the enthalpy of it plus the feed enthalpy plus the heat of the reaction, which is equal to the heat which is being supplied from the surrounding or it has been released in the surrounding. That is, we have to include it. And once you derive everything, you will get an expression with the conversion which is depend on the net heat that is still required after the heat transfer to rise. So that means the actual heat required for the system, that is the net heat divided by the heat released by the system. That is what we will explain here. And if you see in the previous case, you have an isothermal condition where there is no heat is being supplied in and out. So that means whatever the heat it is produced, once it has to go with an exothermic or an endothermic. So that is depend on delta HR. So that is what it's been represented in the conversion versus temperature graphs. And if you see in the non-adiabatic, it is mostly an exothermic because we only see that the system will get absorb the heat or it release the heat. So you need to have a connection between surroundings and the system. So that means there is an exothermic approach. That's the heat should be get away here. So this is the exothermic line and this is the isothermal condition. So if the heat is released, then you will get an additional heat. If the heat is been removed, then you will get a lower heat which is in the system. So that is what the graph is. If you connect the material balance with the enthalpy, you will know exactly at which place the optimum temperature is required. So if you come this place, it is assumed that there is only a small material being produced. That means the conversion is almost nil, the negligible or very low. But if you come into this stage, that means mostly it is been converted. So this could be the temperature, the optimum temperature that will be included here. So just once again. Sorry, my video is off. Okay. So can you see the video now? Excuse me. Can you see? So this was the adiabatic and the non-adiabatic enthalpy balance that we solved it. Okay, but because before I wrote it, unfortunately the power was off, and then I just explained by my notes itself to you. So we need the enthalpy of the system has to be derived, and we have to get in to the conversion versus time. I mean, the temperature is our real parameter that we need to check with our reactor performance here. Okay. So please write this problem. I will come to you soon. Please write this problem, and we will solve this problem. With this problem, we will finish the syllabus today. Sir, any clarification? Have you wrote this problem? Yes, sir. No one to sir. Sir, நானும் முடிக்கல அப்படிங்கற கொஞ்சம் தயவு செஞ்சு சொல்லுங்க. Hello. Yes, sir. No, sir. Sir, Mr. Jnana Arvind. Mr. Jnana Arvind. ஆளையே காணோம். ஆன் மினிஸ்ட் போயிட்டாரா? சரி, மிஸ்டர் கவின் பிரசாத். Mr. Kavin Prasad. Mr. Kavin Prasad. என்ன பண்ண மாட்டேங்கிறீங்க? குமார், நீங்களா ஆன்சர் பண்ணுங்க சார். Mr. Harish Kumar, 35.
Yes, sir.
Thank you, sir. நீங்களா ஆன்சர் பண்ணீங்களா? Sir, question எழுதிட்டீங்களா? The problem actually says that you need to find the equilibrium conversion. So the equilibrium conversion will be represented as a AE, that is X AE. Equilibrium conversion. Similarly, the equilibrium constant will be K, that we will mention. Okay. So the equilibrium constant. So just remember these things: the equilibrium conversion and the equilibrium constant. And this is an reversible reaction which A gives R, and here you keep as a K1 and K2. Okay, so you just fix it K1 and K2. Here the delta G, that is the Gibbs free energy, is given, and the delta HR, that is the heat of the reaction, is given here. It says that the heat capacity of the product and the reactant is constant. So it's actually very good, because if it has a variable thing, then we need to calculate that independently. Then we need to do an enthalpy balance, and they have to carry on here. And what it says that construct a plot of temperature versus conversion. Temperature versus conversion. We need to find the temperature versus conversion here. The one thing is, to do this, we need to first find the K value temperature relation. We need to consider one is the free Gibbs energy. The Gibbs energy, we say, gives free energy, says G T, right? This is the minus that do it, because here we know the delta G. So from this we can find K. Also say that K equal to G. So here the temperature is given. So at this particular temperature, the Gibbs energy is this. So then if you substitute that, you will get the actual to 2.8 degrees. So that's very important here. And here we already have a negative sign, and the negative sign with negative sign will be a plus sign. So this K value will be approximately 300. 300 is the K value from this particular Gibbs energy, which in the next one. Now, the K value, because we have K1 and K2, K value by K1 and K2 equal to delta H. That is the heat of the reaction, or 1 by T2 here, minus 1 by T1. So at the same temperature, 298 degree Kelvin, so we need to find the particular K value here. At K, we say at 298 degree, this is T1 equal to 2. And for this particular K value will be 298 300. Now we say K1 this one. So this is K1, this T1. So now we know T1 and K1, and we know R value, and we know delta H R value. So we don't know this K2 and T2. So that is what we need to do it here. The questions will say that if you substitute this here, then K2 can be written as, because we will put exponential, because all the exponential will go there, and this K1, K like this, K2 equal to K exponential of delta HR minus by R 1 by T2 minus 1 by T1. That is, here T1 is 1 by T. Exponential. We substitute this delta HR here, minus 75300. Okay. R 298. So this is the relation between K and the temperature. Now, what exactly it's asked that we need to find the construction between the temperature and the conversion here. So we, instead of K, because we know that K is dependent on the temperature. Now we have to bring the connection between the conversion and the K value. That is very easy, because we know that the rate equation here. Because previously I was actually explained that K1 by K2 equal to K here. That is actually XA 1 minus, right? It's simple that if you or 1 CA K2, okay, here CA will be equal to CA naught 1 minus XA. And CR equal to CR naught plus XA CA naught. Here C. So CR XA, that means RR equal to K1 CA naught 1 minus XA minus K2 Ca naught Xa. This is what the particular RR will be term will be 0. So then K1 Ca naught 1 minus Xa equal to K2 Ca naught. So now the because at the minus, that's the rate of the reaction, it will equilibrium stage. Equilibrium stage, you substitute you is at the XAE, that is the equilibrium conversion point. So if you rewrite this, then you will get by K, this Ca0 cancel and equal to XAE by 1 minus XA. That is what you actually get here. This is, you will get this. So this is, you write the relation here. Okay. So I'll just drop this one. So we know the relation XAE equal to KAE plus K1. And here you consider K2 is a K here. So K2 is, it's a K, just for our sake. We will keep this as the equilibrium conversion. And if you write this XAE equal to, if you rewrite this term here, X 1 to temperature with K and conversion with K. So that means conversion with now. Not to build the values. You start to assume the temperature. Temperature, for example, 0, 10, 20, 30, 40, 50, 60, and etc. And if you do this, so this is at the degree Celsius, so you put at Kelvin. Kelvin, you say 273, 283, 3, 3, 3, 323, 333, etc. This is at Kelvin T. If you substitute this temperature in this K value, then you will get a K value here. That means what is K value? This particular, if you substitute this in this particular equation, the temperature here, you will get a K value. That is, the K value will be 4, something like that, 149 and 493 180 9 and something like this. So the K value keep on decreases drastically. And if you know the K value, you substitute the K value here and find XAE. That means 0.99, 0.99, 0.998, 0. The 9 0.966 6 0.92 0.85. And if you go with the 80 degrees Celsius, then 0.7. If you go with the 90, it's 0. And So like this, the bond decreases with higher temperature. That means the temperature term will definitely will have an influence here. And once you get this one, okay, you draw the graph XAE versus temperature. 600, and if you say 1 and here 0.5, so the point will be like this initial stage. So the point will be like this. So once you get the point like this, you draw the line. So this is the graph between conversion. Conversion. Once you get it, what is the next one? So now you construct the plot between temperature and the conversion. Next, the next point is what restrictions should be placed on the reactor, on a reactor operating isothermally if conversion is 0.75 degree or higher is desired. That means at 75 degree conversion, if you 5%, draw this. So this point somewhere here, that means it is approximately 78 degrees Celsius is the temperature that is being required to operate the condition isothermally to get a higher conversion in this particular. So you need to temperature will be, it's not in a. So like this, the problem will be there. So this is the end of the session. So now, any doubt that we can discuss about it. Discuss now. Unga roll number. Unga